today's video, we're diving into an exhilarating experiment, breaking down the step-by-step process. Buckle up as we're about to blast off into an extraordinary journey. Stay tuned for an out-of-this-world experience.
First, let's explain the parts and the purposes of our launcher. Solenoid. It regulates gas flow through the use of electromechanical solenoid, which opens and closes the valve. Controller or switch. It is employed to control the opening and closing of the solenoid by providing an electrical current to it. PVC pipe. It is the component that stores the air supplied by the pump. Tire valve. It's the device that directs air from the pump into the PVC pipe tank. End cap. It seals the two ends of the PVC pipe tank. Solenoid valve. It is connected to the solenoid and used to connect a tube on the other end of it where the rocket will be placed. PVC PRP. It serves as the guidance system for the rocket model, ensuring its trajectory and orientation.
Now let's move on to our rocket. Our rocket comprises several key parts, each with a specific function. First is the nose cone. The nose cone protects the payload during the rocket's ascent through the air. We use styrofoam for our rocket since it is simple to form into a cone. Next is the rocket body. It houses the main components and provides structural support. Our rocket's body is made of two linked plastic bottles. Last, the control surfaces, or the fins or thrusters. The fins or thrusters help stabilize and control the rocket's flight. We use corrugated plastic sheet for our rocket's fins, and we went with a 3-fin design with an extra 3 fins on the upper portion of the rocket's body. The rocket's height is 1.44 feet with a weight of 132.5 grams. This model illustrates the arrangement of rocket components in terms of body, design, and structure, consisting of 91% propellant, 6% body, and 3% payload.
Effective planning serves as the cornerstone, translating our vision into actionable steps. Utilizing designs, materials, and essential tools, we embark on constructing the launcher, tank, and sample rocket for initial trials. Through multiple test runs, we refine our approach, aiming for the optimal outcome. Transitioning to the main body, comprising body, fins, and payload, we meticulously apply finishing touches, culminating in a polished project. Now, poised for the experiment, our comprehensive process ensures readiness for a successful venture.
Now let's move on to the result of our experiment. To see the maximum and minimum PSI, height, time, and performance, we decided to do 3 launches. We start with the highest PSI. The first launch is 100 PSI, with the height of 40 feet and lasted 3 seconds in the air with a straight stability. Next is 90 PSI, with the height of 35 feet and lasted 3 seconds and has straight stability too. Lastly, the lowest PSI and lowest height, 80 PSI with the height of 30 feet and lasted 2 seconds in the air. The difference is the stability of this launch is slight straight due to wind, but it was compensated by the fins.
In conclusion, our rocket, utilizing air pressure and cornstarch as propellant, demonstrates a direct correlation between the pressure measured in PSI in the tank and the achieved height. Higher PSI yields greater altitude. The fins play a pivotal role in stabilizing the rocket's trajectory, ensuring a more controlled flight. Occasionally, deviations from a straight path can be attributed to strong winds, influencing the rocket's course in the air. Overall, our innovative design emphasizes the interplay of pressure, propellant, and aerodynamics for optimal performance.
Thank you for joining us on this thrilling journey with our air pressure powered rocket. If you are as inspired as we are by the wonders of DIY rocketry, hit that like button, subscribe for more rocket fueled content, and share your thoughts below. Until our next launch, stay curious and keep exploring the skies.